Hey guys, it's me, Miss Miller. Just wanted to say hi and show my face. Hope you're all doing well and are picking up on the content. Always email me if you have any questions. I am gonna exit out here. Okay. Miss you all. All right, we are gonna finish chapter 5, not chapter 5, chapter 5.1, dealing with angles and radian measure. We're going to focus on coterminal angles as well as the arc length of a circle. So, by definition, a coterminal angle are two angles with the same initial and terminal sides but different rotations. And what that really means is that there can be an infinite amount of coterminal angles. So if we see the example here, we have an angle in standard position. This is still my initial side. And if I read it to the terminal side going counterclockwise, the positive direction, we have 120 degrees. But sharing the same terminal side, if I went counterclockwise, I have negative 240. As I said before, there's infinite, and you might be saying, well, there's only two. How is it infinite? Well, when we think of a rotation around going a full 360 or 2 pi radians, you could have an angle like this. So we could have the initial side being our positive x-axis, our terminal side in the first quadrant, and one of the angles being 45. What's coterminal to that would be negative 375, or with a full rotation around, plus an additional 45 would give us 405. And we could keep doing this. We could keep having rotation after rotation after rotation, same with our negative. So that's why we have infinitely many coterminal angles. When you're asked to name a coterminal angle, a lot of times it's restricted to just a positive angle between 0 and 360, or just a positive angle or a negative angle. You'll get direction on that. But the idea here is that coterminal angles share the same initial and terminal side. It just is a rotation whether we go in the clockwise direction, being negative, or in the counterclockwise, being positive. So algebraically or numerically, we find coterminal angles by increasing or decreasing the degree given of the angle in standard position with an integer multiple of 360. So you're adding a full rotation, going counterclockwise or clockwise by subtracting. So we can think of this as just taking your angle that was given, and you're going to either add 360 to it or subtract 360 to find a coterminal angle. The same can be said with radians, because again, this is just dealing with degrees. A full rotation in radians is 2 pi radians. So to find a coterminal angle using radian measure, you increase or decrease the radian measure of an angle in standard position with an integer multiple of 2 pi. The reason we're saying integer multiples is you can do more than one rotation. So if I did a full rotation, two full rotations in degrees, I'd have 720 degrees. If I did two full rotations in radians, I would have 4 pi. So you can do this an infinite amount of times, and we're going to see examples like this in the upcoming problems. Again, we would take our theta, add or subtract 2 pi to get a coterminal angle, because we know our angles can be positive or negative. So let's take a look at these examples. We're going to first dive into with a degree measure. So assume that the following angles are in standard position, our positive x-axis as our initial side, and then our terminal side. Find the positive coterminal angle less than 360. What positive coterminal angle less than 360 means is that the angle we're finding is between 0 and 360, not equal to 360 though. So if I take 370 degrees, I know that that is more than 360. It is more than a full rotation. So I'm going to want to subtract 360 to get a coterminal angle between that. So I'll have 780 degrees, and now I'm going to be subtracting 360. When I do that, I end up with 420 degrees. Now that is a coterminal angle to 780 degrees. However, it does not fit our directions that say it has to be between 0 and 360. So that's where this multiple, so you can subtract again 360, and now we get 60 degrees. This is the coterminal angle. It does not have to be acute, it just has to be between 0 and 360. So if we take a look at the image here, we can see that 780 degrees is 2 full rotations plus 60 degrees. If you had wanted and you recognized that it was more than 2 full rotations, knowing 2 full rotations was 720, you could have just done 780 minus 720, and you would have still gotten 60 degrees. Either way, these are all coterminal angles because they share the same terminal side. We would not want to say negative 300, although that is equivalent, it is not positive coterminal based on our directions. So you have to be careful and make sure we read. Okay, here is our other example. I learned how to color code, so I'm going to do that today. We have negative 245 degrees. So since we want a positive angle, I'm going to go and add 360 to this. So I have negative 245 degrees plus now 360 degrees, adding a full rotation to this. And when I do that, I end up with 115 degrees. Again, not an acute angle, but it does fit that theta would then equal my coterminal angle, 115 degrees, making sure I put that symbol, otherwise it can be construed as radians. And for an infograph, here we have negative 245 that was given, and so my coterminal angle is 115 degrees. So now, radians. I do not want you converting radians to degrees to figure out the coterminal angle, but rather just adding or subtracting 2 pi as defined in the previous slide. So here I have 19 pi over 4, which is more than 2 pi. 2 pi here would be 8 pi over 4. So what I'm going to do here, since it's larger than 360 or 2 pi radians, is I have 19 pi over 4. Actually, I think I did this already. Hold on. Let's see. Yes, I did. Okay, 19 pi over 4, and we're going to subtract 2 pi. And in order to do this correctly, we need to get a common denominator of 4. So I have 19 pi over 4 minus 8 pi over 4, giving us 11 pi over 4. Now, it's really important to know that 11 pi over 4 is not between our directions 0 and 2 pi radians. So knowing that's a positive coterminal angle, it is positive, but it's more than 2 pi. So what do you have to do? Subtract again. Since we already made a common denominator, I can just subtract 8 pi over 4 from 11 pi over 4, and I get 3 pi over 4. This is my coterminal angle. To give you a little bit of a visual, 19 pi over 4 is 1. 2 full rotations plus 3 pi over 4. Again, if you recognize that it was 2 full rotations, then you could have just subtracted from 16 pi over 4 to give you 3 pi over 4. It's up to you. All right, our next example, a negative angle measure. We want to find a positive coterminal angle. So we're going to start off by now adding, because again, we want it to be positive, it's negative. So I add a full rotation, 2 pi radians, getting a common denominator to be 6 pi over 3. Negative 4 pi plus 6 pi gives us 2 pi over 3. That right there is between 0 and 2 pi. So my coterminal angle is 2 pi over 3. an image to show you. This is just like the very first example I showed you. 2 pi over 3 is 120 degrees. And so negative 4 pi over 3 is negative 240. But as you can see, that would be my coterminal angle. Not every time is it a multiple rotation, but sometimes it's a negative. And it can be a negative multiple rotation as well. Now that we have an idea of coterminal angles, it's important for us to look back at our definition of radians to understand how to find the length of a circular arc. So if we use our radian measure formula, theta equal to S over R to find the length of an arc of a circle. You can also use this formula to find the radius, or if you're given theta and S, or if you have, if you're given the arc length or the radius, you can find the radian measure. But again, it's important to remember that this formula is what we use to find radians to begin with. So when we're finding arc length, we have to remember that theta is in radians. S represents the length of the arc intercepted by the central angle, and theta is always in radians. I can't say that enough. So again, here is an image for us. We have our central angle. We call that theta. Our arc length is S, and R is our radius. S equals R over theta. It's the same formula, just multiplying R to both sides. They're equivalent. So let's go over an example. A circle has a radius of 10 inches. Find the length of the intercepted arc by a central angle of 120 degrees. Does anyone see a potential problem? This is where I would expect my students to be like, hey, that's degrees. Yes, it's in degrees, but since we know how to convert to radians, that's what we're going to do to use our formula. So what we are given is we know we're trying to find this arc length right here, S. We are given theta, not in the right unit measure, but we will get there, and radius. So we are given that R is 10 inches and that theta is 120. So let's first go ahead and convert to radians. The way you convert is pi radians over 180 degrees. So I take theta equaling 120 and multiply it by my unit conversion. So I end up canceling out my degrees. So now I have 120 pi radians over 180. Very easy. You can cancel out your tens place. So you have 12 over 18, which reduces to 2/3 pi radians. Now you can put the pi next to it or keep it in the numerator. That's fine. Now you know what your theta is to use for our formula. So to find our arc length, that is the direction here. We can then say S equals theta times R. So S is going to equal 2 pi radians times our 10 inches. We go ahead and multiply. So then I get 20 pi over 3 inches. Now this is exact. But most of the time we don't describe inches in terms of pi. So we can then round to say 20.94 inches. I hope that this video is helpful for you and do your work on Delta Math. As always, please feel free to email me or reach out to me on Google Classroom. I hope everyone's doing well and I miss you.